Okay. So yeah, so the first, like the only one that I discussed yesterday, which one's the characteristic type of reaction for aldehydes and ketones? What type of reaction do they undergo? Because so this happens because of the polarity of the C double bond O, this particular part of it.
Nucleophilic addition.
Nucleophilic addition, that is correct. Here, nucleophilic addition. So what happens is, just like simply put, you have C double bond O, carbon पे there's हल्का सा positive charge, oxygen पे there's हल्का सा negative charge. So when a nucleophile attacks, that's going to go attack the carbon atom, and then whatever H plus the iska counterpart is there, that gets bonded to the oxygen. So the trigonal planar ends up forming into a tetrahedral intermediate. Okay. So this set of reactions, the first example, or the first reagent that we'll be looking at would be with HCl. So all these reactions, this will be the main mechanism. So each of these examples will only be looking at some extra information, where it might be used, for what purpose that product will be used, and the name of the product. So that's mainly the points we'll be looking at. Okay, so if HCN ke case mein, this is pretty simple and straightforward. Which one will be the nucleophile? HCN mein what
Cn minus.
CN minus, absolutely. So Cn minus is the nucleophile that goes and attacks carbon. So what you end up getting, so this will be your intermediate. Carbon in the center. You have these two bonds are default, jo bhi hai. Then Cn is attached. Oxygen pe you have a minus charge. And HCN may this ionizes into H plus and Cn minus, right? So the H plus that is there goes and bonds with the oxygen. So your final compound that you get looks like this. So this product, where you have alcoholic group and a nitrile group, Cn and OH. So this class of compounds, they're called cyanohydrins. Okay. So this particular reaction, extra point that we need to note is this is catalyzed by a base. So this particular reaction happens in basic medium. And the reason why, like if I use NaOH, Cn minus is the will be the attacking species rather than OH minus. That is because Cn minus is a stronger nucleophile than OH minus. So when you have both the species in the same solution, Cn minus will be the nucleophile that will attack. So there you won't get that conflict of, okay, why not OH minus? All right. Simple, like let's do a couple of examples based on this. What happens when acetone reacts with HCl? So suppose I have CH3, COCH3 plus HCN. Give me the final product that you get. So are you sending the structure on, like, do you know the name, or are you sending the structure on chat?
Structure on chart.
Okay. There you go. That's it. Simple. Kaveri and Smera have gotten it. See. So the name of the cyanohydrin, you just like call it whatever you start off with and then put cyanohydrin there. So because we are starting off with acetone, the name of this compound, just call it acetone cyanohydrin.
Is there a
Common
space between the two?
Yeah, one of you. Okay, Kaveri, yeah, go ahead.
Wait, I thought she's going on. Is there a space between the two, in between acetone and cyanohydrin, or is that one word?
No, you put a space there. It's not the IUPAC name, obviously, because IUPAC will involve hydroxy and cyanonitrile. So if you start with acetaldehyde, it's just called acetaldehyde cyanohydrin. Smera, you're out?
My doubt was that only it's common or IUPAC.
Like common name. So this will be Sanskriti, you're yet to send.
How should I send it on chat?
What happened?
How should I send it on chat, the figure?
Yeah, anyway, you can just type out the structure on chat. So whenever you have like multiple this thing, put it in brackets. I'll be able to get that.
Yes, ma'am.
Okay. So Arya, we just started off. This is the first reaction we did, reaction with HCN. So this means CN minus is the nucleophile. It's pretty simple. Just a couple of points. Need to know the product. They're called cyanohydrin. And the fact that these reactions are catalyzed by a base. So sometimes if you get HCN in the presence of NaOH or OH minus, don't be confused. OH minus just catalyzes it. Between Cn minus and OH minus, Cn minus is a stronger nucleophile, so that will be the one attacking the carboxy group.
And this is on the chemical properties, right?
Yeah, this is in the chemical properties. The first reaction we're looking at. Okay, Sanskriti is sending quickly.
How is it acetone cyanohydrin?
Because we started off with acetone. So if we are doing this reaction with acetaldehyde, it'll just be called acetaldehyde cyanohydrin. Formaldehyde cyanohydrin. That way. Yes, absolutely. Yeah, so you're going to have carbon central atom. These two CH3s will be retained as it is. And you get OH, double bond becomes single bond, and CN gets attached to carbon. This is the structure. Okay. Why did we pick this as an example? Cyanohydrins, they're basically used as intermediates to manufacture other things. Like the way we've seen a lot of preparation reactions with acyl chloride, right? So acyl chloride, you can use it for Friedel crafts to put C double bond on benzene. You can prepare aldehydes from it. You can prepare like ketones from it by treating it with Grignard reagent. So that way, cyanohydrins are also intermediates in order to prepare other classes of compounds. So on oxidizing it, like on acidic hydrolysis, you end up getting alpha hydroxy acid, like salicylic acid and all. On reducing it, treat it with lithium aluminum hydride, you end up getting amino alcohols. So this gets reduced into an amino group, and then you have an alcohol group in that same compound. So it's basically a middle intermediate to prepare other classes of compounds. Okay. Next one, we'll still in nucleic.
1 second, I was just on the last line.
So by the way, Esther, since you were discussing about
The name of the product is acetone.
cyanohydrin.
Yeah.
Cyanohydrin. This is the common name, not the IUPAC name.
Yeah. Okay. Got it.
So since we were talking about formaldehyde yesterday, so there's a whole process called tissue fixing or fixation. So how it acts in preserving is two ways. One, it kills bacteria and like other microbes, as I thought yesterday. It's like, yeah, it prevents the decay through other organisms. And second, so aldehydes, they react with the cell cut tissue, like they denature the protein in a way where the structure is preserved. So that's why, like it's so that way the cells and tissues can be preserved as it is. That's where formaldehyde is used. Think of an egg. Like you denature the protein when you cook the egg, right? And then the structure becomes like rigid, becomes a solid. So that's what it does to the living tissue. Okay. Anyway, back to nucleophilic addition. Next one is NaHSO3, sodium bisulfite or sodium hydrogen sulfite. So isme, you guys predict what the first step of the product going to be. So we start off with either aldehyde or ketone plus NaHSO3. So intermediate, like, okay, which one bonds to carbon, which part bonds to oxygen? What do I get here?
ONA and SO3 minus.
ONA and HSO3. The hydrogen is also there, right?
Yeah, sorry, I just.
Plus, and this will be negative. So this is the intermediate that you get. And this will undergo a proton transfer. Actually, it's a little bit of, let me put it this way. Sulfur is the one that bonds here. So this will be SO3H. So this will undergo proton transfer. So the final product is going to be OH and SO3Na. So basically the sodium and the hydrogen atoms exchange places. Okay. So yeah, this is the thing. So the reason why we study about this, the significance of this particular product is that this is used in purification of aldehydes. So what happens is you suppose you have a sample of aldehydes or ketone, treat it with this particular solution, the salt solution, sodium bisulfite solution. Then when you do acidic hydrolysis, acidic or basic hydrolysis. So basically this particular compound, OH and OSO2Na, to be even more specific about the bonding. So when you treat this with dilute mineral acid or an alkali, acidic or basic hydrolysis, so or an alkali, you end up getting your aldehyde or ketone back. So that is why this particular reaction is used in purification of aldehydes. Okay. So that is the thing. Another point about this reaction, again, we use it in purification of specifically for aldehyde because the second step, no, actually, like the first step itself, this is a reversible reaction, right? So this reaction favors aldehydes more strongly, like equilibrium is pushed towards the right for aldehydes and on the left for ketones. Iska equilibrium is pushed to the right for aldehydes. Basically, aldehydes favor this reaction more than ketones do. Can you think of a reason why? Why are aldehydes more receptive with this reaction?
Because presence of O. Okay, there's a ketone
Presence,
also.
absence of
H plus H in ketone.
H compared to ketone, which has the R,
Yeah.
which provides steric hindrance.
Due to steric hindrance reasons. Steric reasons. Yeah. So bulkier the group, less reactive. Like this is true for most, like we discussed reactivity yesterday, that aldehydes are generally more reactive than ketones because of steric reasons and plus effect. But within aldehydes, ketones also, the bulkier groups that are present, like attached to carbon, the less reactive they are going to be. Okay. So 2 points. One is reactivity between aldehydes and ketones. And the second is, where is this reaction used? Used in purification of aldehydes, because you basically treat it with the salt and then treat it with your acid or alkali again, you get your aldehyde back.
For all nucleophilic addition or substitution, this is the main difference between aldehydes and ketones, right? The fact that there is more steric hindrance for ketones.
Yeah. Substitution nahi hoga, but like addition, yes.
Whenever we say SN1, SN2, so definitely we'll SN2 will definitely take steric hindrance into consideration, right?
Yeah, that was, yeah. I mean, that's for the species that undergo substitution reaction. Aldehydes ketones will not undergo substitution, no. They will undergo addition only. Haloalkanes will undergo substitution. Haloarenes will not.
Sorry, can you explain the proton transfer again? Didn't understand. Like the reason.
Reason nahi, like again, because you will be taking the solution of like salt. This is a salt, right? So you'll be doing this reaction in the salt solution. So what happens is once this product is formed, um, this is going to get converted into alcoholic group OH, and this is going like ag- because again SO3 is more electronegative. Like it's a anion. It's a derivative of sulfate or sulfide ions. So this is going to have Na plus bonded to it. So essentially, the net result, what you can see here is that the hydrogen and sodium atoms have exchanged their places. So this particular process, so we call it proton transfer because the H plus has been transferred from here to here.
So this is to like attain stability.
Yeah,
But how is NaSO3 stable?
derivative of like this is sulfate salt, no sulfide salt. Right?
Like Na2SO3? Acha.
So yeah, that is this thing. The next
Ma'am,
one.
wait.
Student, right? Okay.
The one that you've written in red is like the process, like this process is used for purification of aldehydes.
So if like in the purification, this is the additional step that you undergo. Wash it with some dilute mineral acid or an alkali, and you get your aldehyde back.
First
But
one,
what? I didn't understand for purification.
Because you're getting your original one back. So this particular reaction can be undergone.
Yeah.
So if you have other
Okay.
ketones or other groups mixed in it, they are not going to undergo the same reaction. So you like again, because this is a sodium salt of a sulfonate, this will precipitate out. So you separate out this particular compound, and then you can regenerate your original reactant, original aldehyde back. So that's how you like whatever other impurities that are there, you won't get them along with that. This you can separate by filtration or crystallization techniques, and can get your original thing back.
Yeah, got it.
the first one was HCN, no? This NaHSO3 is the second. The first one was HCN.
Done?
One second.
Yeah, you can note this down. So this is a crystalline salt. So you dissolve this in water, separated from the other impurities, and then yeah, once you separate it, treat it with like basically hydrolyze it, you get your aldehyde back. That's how you verify.
How CO is used in purification of aldehydes?
CO what? Where is
CO. What you've written used in purification of aldehydes.
not the product. I'm talking about this whole process. Like because of this reaction, like basically this reaction is what you do uh, during purification of aldehydes. This is one of the methods you can use. If you can't get your original thing back, then there's no point. I mean, obviously, you can't purify aldehydes based on that. But because you can get back the original aldehyde, uh, and this particular product has the special property of being crystalline, so it's easy to separate this product out and then get your original aldehyde back. That's how we purify.
I understood the steric hindrance ka reasoning, but I didn't understand how that means right or left for aldehydes and ketones.
Simple. Equilibrium shifting towards the right means the product is favored more. Matlab forward reaction happens a lot more. You get more yield in this product. Equilibrium shifting towards the left means reactants are favored more. मतलब इतना products form नहीं हो रहे.
ओ तो क्योंकि कीटोन में स्टेरिक हिंड्रेंस ज्यादा है तो इट वोंट फेवर द रिएक्शन, तो वो लेफ्ट की तरफ होगा. Yeah, done.
None? Cool. Okay. The next thing we'll be looking at is reaction with Grignard reagent. This should be very, very easy.
Didn't we do this like just a while ago?
No, Grignard reagent is used in a lot of places.
No. In this chapter only, we did some Grignard reagent ka reaction, no?
Yeah, preparation में. Okay. All right. So this plus say RMGX. What is the what do you call it? Intermediate going to be?
Where did we do Grignard?
Use
Somewhere we did the preparation में RMGX का. Hold on.
ketones. Remember, Grignard matlab you're just adding an extra R group somewhere. Like that depends on what you're taking in the first place. So
We did in preparation of ketones from acid chloride and nitriles.
yeah, that tags on the extra R, and whatever chloride or nitrile group you have, that gets oxidized to oxygen. That's how you prepare it. Okay, so यहाँ पे what will be the intermediate? C. Yeah. What's attached to oxygen?
MGX.
MGX.
Yeah, and the hydrocarbon bit gets attached to carbon. So the reason, again, this is used in the manufacture of alcohols. So this on hydrolysis end up getting OH and R plus MgOHX. So the importance of this is, okay, so the final product. So suppose you start with an aldehyde. What sort of an alcohol will you end up with?
Primary.
Check again.
Primary.
Secondary. Secondary, right?
Secondary.
Because you're getting an extra R over here. So if one of them is an H, one of them is an R, you end up getting secondary alcohol. And if you start off with a ketone, then what do you get?
Then we get tertiary.
Tertiary alcohol, yes. If you want a primary alcohol by this method, what do you need to use?
Carboxylic.
How do we know that it is like R, the other one? Like one is H because that is aldehyde gas. What about the other one?
That's
How
what
do we know that it's
your control, no? It depends on what you're taking here in the first place. So let me color code.
That is only structure
So-
of aldehyde.
So if I start off
yeah,
with
so if it's not R, then you will get primary, na?
if
How it will not be our aldehydes में होता ही है ना H.
yeah, there's a
H is there. The second one, if that is also H.
if I want a primary alcohol, then what should I start off with? Reverse engineer it. So primary matlab
You
yahan
need to
yeah, go ahead. Yeah. C H2 होना चाहिए because then there's only one carbon chain and this becomes a primary alcohol.
So if we start with methanol, then we will get
Methanol,
primary
yeah.
alcohol. Right?
yeah.
To start with methanol or aldehyde.
So that's an exception, right, to aldehyde giving secondary.
Only with methanol because it has both hydrogens. Any other aldehyde that you take, it has an extra carbon chain, so this ends up being a secondary alcohol. Okay. Yeah, so this would be a method of preparing alcohols. So again, because you're starting off with Grignard reagent and the aldehyde is in your hand, you lots of customization possible. Like you can create any type of alcohol just by controlling this and this. Like yeah. You can modify this. So acidic hydrolysis, H3O plus or H2O and H plus. So this will get oxidized. H plus goes here. End up getting this. Okay, so let me know when you guys are finished with this. The next one is going to be a little new class of compounds will be introduced. Actually, I'm gonna do it in the next bit. So you done this? Okay. The next one is addition of alcohols.
Wait 1 second.
Oh, even I was.
Done.
See, Arya?
Yeah, me too.
So we'll look at addition of alcohols. Okay, there's only a minute left. So because there's like a special name for these class of compounds, we'll do aldehydes and ketones separately. Okay. So aldehydes, let's take our C double bond to H plus ROH. So this reaction is done in the presence of HCl gas. What will the intermediate look like? So R will remain as it is. C here. H will also be there as it is. Oxygen hai. And then there's like obviously when the bond breaks, you have an extra thing. So what part is attached to oxygen and what part is attached to carbon? How does this bond break? Well, does it break at OH or does it break at between R and O?
Between OH or between?
R and O. Like which one will be the nucleophile?
OH minus.
Minus.
OH minus.